Hi everyone. We are looking at our second problem here under proof by exhaustion. The question says, prove that for any integer x, the value x cubed plus x plus 3 is an odd integer. The value x cubed x plus 3 is an odd integer. We know what integer numbers are. They are just counting numbers. 0, 1, 2, 3, 4, 5, without decimal points, no fraction. These are integers. We call those numbers. And we know what an odd number is. A number that is not divisible by 2 is an odd number. A number that is divisible by 2 without any remainder left is an even number. For example, you have 1, 3, 5, 7, 11, 13, 'These are odd numbers. I've jumped 9. These are odd numbers. But when you have 2, 4, 6, 8, 10, these are even numbers. Yeah? These are odd numbers, these are even numbers. Our proof says, prove that for any integer, that any number x from this equation here, whatever number you represent with x, if you then calculate this function, if you take x to be 1, so this is going to be 1 raised to the power of 3 plus 1, that is 4 plus 3, 7, so you get a total of 7 if you take x to be 1. If you take x to be 2, you get a number. If you take x to be 3, and they say prove that that number that you take, when you calculate this value here, what you get is an odd number. It's an odd integer, an odd number. What you get, the number you get will fall under this category, not this one. So looking at the question itself, you know now when you want to prove this by exhaustion, you have 2 cases to prove. It splits the problem into smaller cases, but you have 2 main cases here to prove. What are these cases? One is odd, one is even. You try to show that this integer is odd, or you try to show that the integer is even. From what you get from these 2 cases, then you can make your arguments, give your answer. So let's try and see. Now, case 1. If x is odd, let's start with the even first. X is even. If x is even, it means x is equals to 2, let's say 2k. If it is even, any number that is even, that number must be divided by 2, or is a multiple of 2. That's what we just demonstrated a few moments ago. Odd, even case and odd case. You can see that all the even numbers, 4, 6, 8, they are multiples of 2. This is 2 times 2, 2 times 3, 2 times 4, 2 times 5, 2 times 6, 2 times 7. So they are multiples of 2. That's why we say we represent x by 2k, where k is an integer. Yeah? This k is an integer. We don't know what k is. K can take any number. But we are making a proof. When you make a proof, you use letters to generalize your case. You don't restrict yourself to numbers. Numbers can easily be calculated, and they know the true value. But when you put a letter here to represent something, then you will be able to generalize your case. So here you can say where k is integer. Yeah? So if that is what we represent x for, 2k, now let's come to this value now and try to see whether the even case works. So now we got this function here, x cubed plus x plus 3. Let's substitute 2k wherever we see x. So here we'll have 2k to the power of 3 because we have x cubed, plus here is just x, 2k plus 1. Yeah? And then this will give us, if we expand this now will give us 8k cubed plus 2k plus 1. Now this one here, we can bring the 2 because we say even case. 2 into 4k cubed plus k plus this 1. Everything here, k is an integer, so everything here is integer here, but it's a multiple of 2. What is here? So everything here is even. This one here is even, but it's added 1 to it, so that makes it odd. That makes it odd. Because of this one added to even number, it makes it odd. So our case for 2k, for the even case, we've proven that the result is an odd number we get. Now, let's go for the case number 2. This is odd, yeah? Because of this one, odd. Now, case number 2, that is when x now is odd. If x is odd, how do you represent odd number? If x is odd, it means you have 2k plus 1. That is odd. 2k let's say x 2k plus 1, because 2k is even. The k, whatever be the value of k, it is always multiplied by 2, so it means it's a multiple of 2. So this is even. When you add 1 to it, it becomes odd. So that is why the odd case is 2k plus 1, and the even case is just 2k there. So now let's put 2k plus 1 wherever we see x in this value here. So now we have here x cubed, so which is 2k plus 1 cubed plus 2k plus 1 x plus 3. There's something big here to do. There is a simple way of working out this function here, 2k plus 1 raised to the power of 3. One way is to multiply. You do it like 2k plus 1, 2k plus 1, 2k plus 1. That is what it means. 2k plus 1 times 2k plus 1 times 2k plus 1 plus 2k plus 1. That's what it means. So first you multiply these two, find the answer. That answer you multiply by this one, then you get your final answer, then you add this. That is the long method. When there's a shorter method, you can use binomial expansion. After this topic, that will be the next topic, binomial expansion. When you have something like this, how to give the answer directly without scratching your head. And you have something like this. If you have a plus b all raised to the power of 3 using binomial expansion. You now have here a cube, first one, and put your plus here, b cube. These two have to have cube. Then what is inside? Now you put 3 because this is 3. A square b plus 3 a b squared. For this one, even if you use Pascal's triangle, you can still solve this because this number is not big enough to give you trouble. Square plus 3ab square. So this is what you get if you expand this. We shall do more of this in our next topic, which is binomial expansion. We'll do the various types of methods to expand a function when this power is high. If you have like 10 here, power raised to the power of 10, you can simply use this to do that. So let's use this method, one here, to multiply this out. Yeah, here we have our a, which is 2k, and our b, which is 1. A is 2k, b is 1. So now to expand 2k plus 1 all cube, a, which is 2k, now you have 2k cube plus 3 a again. So this is 3 times, which is 2k squared, because it's squared here, b, and b times 1 plus 3, a is 2k, then b squared, which is 1 squared, plus b cube, which is 1 cube. You have used binomial expansion to do this. So if you now expand this, you will get 8k cube plus, this is 4 squared, 4k squared. So 4 times 3 is 12. So 12k squared times 1 is just 12k squared. Plus, this is 6k times 1 squared is 1. Plus 1 cube is 1. So this is what you get. So you get this function like this. But to complete the problem, you just expanded this. Now you have this whole equation. And you know this equation has 2k plus 1 plus 3. Or plus 4 here. Yeah? 2k plus 4. So now the entire equation now will give you all this 8k cube plus 12k squared plus 6k plus 1. Now I'm adding this 2, this 3, yeah, plus 2k plus 1 plus 3. So this is 1 plus 1, 2 plus 3, this is 5. Yeah, and this will give you 8k because 2k plus 6k, so this now will be 8k plus 5 here. So I'll put 8k plus 5, the whole thing. 8k plus 5. So what are we trying to prove? We're trying to prove that this case is odd. Okay? So, what do we do? Maybe should get 1 somewhere. This multiplication. Why should we get 5? In this case, let's do our multiplication the normal way. This is a topic we haven't done yet, so let me don't use it here. So now we are cross multiplying. we are multiplying this 3 times. So this one here, this times this is 4k squared plus 2k, 1 times 2k plus 2k, 1 times 1 plus 1. 2k plus 1 plus 2k plus 1. No. 2k plus 1. Yeah, plus 3. See? Plus 3. Oh, yeah. 2k plus 1 plus 3, yeah. Yeah? 2k plus 1 plus 3. Yeah. So now we got this. So this means this is 4k squared plus 4k plus 1, all multiplied by 2k plus 1. And this one will give us plus 2k plus 4. 2k plus 4. We are bringing down this equation. This is 1 plus 3 is 4. That's why we have 4 here. This 2k is k. Yeah? Because here we've said let x equals to 2k plus 1. So we have 2k plus 1 all to the power of 3 because of this. And x is 2k plus 1 and this 3 here. So we are just representing this value here. Then we just start to expand. That's all we are doing. So now we multiply this by this. So 2k times this, so you get 8k cubed. 2k times this plus 8k squared. 2k times 1 plus 2k. You now do the 1. 1 times 4 plus 1 times 4k plus 4k squared. 1 times 4 plus 4k. 1 times 1 plus 1. Then you have plus 2k plus 4. Right? So now you have this and this will give you 6. Let's start there. We have 8k cubed plus 8k squared plus, no, you have 4k squared plus 8k squared. This will give you 12k squared. Yeah? We're adding like terms, this and this, k squared, k squared. So this gives you 12k squared. So now you have k squared plus this. So this gives you 6k. 4 and 2 is 6. So now we have another 2 here. 2, 4, 2. So 8. This gives you 8k. You have this one, this one, this one. So 2, 6, 8. And then you have plus 4 plus 1. You have 1 here. You have this 4. I could have added it to make it 5, like the previous one we did. But since we did binomial expansion, maybe some people are going to get confused if I try to split that 5. So that's why I came to this method here to see the 1 and 5. They are not, we don't want to add them together. We want to do something else. It's got something we want to prove. So here, what can you see? You can see that 2 can divide all these numbers here. 2 is a multiple of 8k cubed, 12k squared, 8k, and 4. So now let's do something here. We take 2 out, and then we put 4k cubed plus, this now will be 6k squared plus, this will be 4k plus, this now will be 2. We close our brackets and we still have our 1 here outside. Can you see that? What are we trying to do here? This k we said is an integer. It's a positive whole number, or is an whole number. A whole number, that is the meaning of integer. It's a whole number. So whatever this number is, if you put k here to be 1, whatever number you get here, it is a multiple of 2, because you already have 2 outside multiplying everything inside here. So whatever number you get here, no matter how small or big that number is represented by k, what you get is always a multiple of 2. So then, this is an integer added with 1. So that makes it odd. This is, we prove again the odd case. We've proven when x is even, the result is odd. Now, if x is even odd, the result again is odd, because 1 is added to it, makes it odd. So therefore, we have proven our case by the method of exhaustion, that this value here is always an odd integer. Thank you for watching. Bye-bye.